Okay, so now let's work out the solution. So hopefully you had a chance to take a crack at it, right? So we are going to use Gauss's law, which states that integral E dot ds, right? This is equal to q inside upon epsilon naught. Q inside is the charge inside the Gaussian surface, right? So let us first start with the first problem, which is for distance x outside the sphere, and here I will draw the same thing here, but I'll make it smaller just so I can accommodate. And so let's say this is my sphere, right? This is my sphere, and this is the radius r, capital R, and this is the Gaussian. So this distance, let us say, is x. This is x. Now I'll draw a Gaussian surface here, right? And I'll choose the Gaussian surface to be again a sphere around the same center, right? So this would be a sphere like this, right? This is a sphere, same center, and now I'm going to apply this particular law to this Gaussian surface, right? So now let's do that. So let's say I take this particular point, right? Now I want to find the electric field here, E. So first question, what is the direction? Right? So again, I'll not repeat the full argument, I've done it in previous videos. So because of symmetry, the electric field will be outside this, right? So it will point in this direction, right? In fact, if I take any point, I take a point here, it will point along the radial line, right? So it's always pointing outwards, and if I take a small area on the surface here, that also will have the same direction, right? So E and ds will have the same direction, angle between them is 0, and therefore E dot ds, right? E dot ds would be equal to E ds into cos of 0, which is nothing but equal to 1. So this is going to be equal to E ds, right? And this will be true for any particular point. And now therefore we'll apply this whole thing. So we'll say integral E dot ds equals integral E ds, and E is constant. Right? E is the magnitude at each point. E is constant. Again, why constant? By symmetry. No, it's a sphere uniformly charged. So this point is no different from this point. So each of them would have the same magnitude. So I can take E as constant. So this would be E into integral of ds. And what is integral ds? This is the total surface area. Now if this distance is x, right, which means the radius of this sphere is also x. So ds is going to be nothing but area of this sphere. So that would be E into 4 pi x square, right, into 4 pi x square, and this is going to be Q internal, the charge inside upon epsilon naught, right? What is charge inside? Do we know the total charge Q? We know indirectly, not directly. So how do we know? We know that rho is given. So rho is charge upon volume, right? So rho is equal to charge upon volume. So charge will be equal to rho into volume, straightforward, right? So we'll say, so this would be, charge would be equal to rho into volume. Volume of what? Volume of this sphere. So it will be 4 by 3 pi r cube, correct? And this would be, and we would say this divided by epsilon naught. This is my Q, right? So once again, E is this, the electric field, we're trying to find this out. 4 pi x square is the area of this larger sphere. This is equal to total charge upon epsilon naught, and total charge here inside is going to be rho density into this volume, which is 4 by 3 pi r cube, right? So now just simplify this. We'll say E is equal to, I can cancel this 4 pi and this 4 pi here, right? So now I'll get my electric field as rho, right, into r cube, right, from here. So 4 pi is cancelled, r cube divided by, we have 3, here we have epsilon naught and we have x square, right? So I'll say 3 epsilon naught x square. So this is going to be my electric field. This would be my electric field. Okay, and this is for this rho which is outside the, this x which is more than the radius of the sphere. Now let's go for the next case, which would be when we have small r which is inside the sphere. Point number B, right? So this was for A, point A. Now we'll find for point B. Right? So what would that be? Same logic. Now I'll take a Gaussian surface inside this. So I'll not draw it again, I'll just show it here. to save some space. So let's take a Gaussian surface. Okay, this is my Gaussian surface. Same logic, I'll not repeat it, right? I mean, at every point by symmetry, electric field at any point is going to be outside. My ds also will have the same direction, right? So angle between E and ds is going to be 0. Cos of 0 is 1. Therefore, we'll say that integral E ds, right, is equal to q internal upon epsilon naught, and this would be equal to integral E ds, and E is constant, so take it out, and ds would be an integral, so this would be E into integral of ds is equal to q internal upon epsilon naught, right? And what is my integral ds? That's going to be the surface area of this sphere, which is a Gaussian surface, and this is going to be 4 pi r small r square, right? This would be E into 4 pi small r square. This is equal to q internal. Now here is a small thing, right? Can I, here this charge, is it same as the charge here? No. Why? Because here the whole charge was inside. Here only this charge counts as my q inside, because the remaining charge is outside. That is the key, right? And how much will this be? So charge is going to be, again, would be rho into volume. So just take the volume of this. So this would be equal to rho into 4 by 3 pi small r cube. Okay, 4 by 3 pi small r cube, and this whole thing divided by epsilon naught. And as we did the last time, we will cancel this 4 pi and this 4 pi, right? Divide by 4 pi each, and then this r square will go to the denominator, and this r square and r cube I can cancel 2 powers of r. So I will get E equals rho into r cube divided by 3 epsilon naught into r square, right? And now I can cancel this r square, and here I'll have only r left. So now I'm getting E equals rho r upon 3 epsilon naught. So this was for case A, this is for case B, right? And this is how we apply this, right? So hopefully this will make sense. Just go through it carefully. Thank you.